Hi, and welcome to our Vulnerability Research and Fuzzing course. Throughout this training, we will learn about finding vulnerabilities and zero days on Windows code on x86 64 processors. We'll look at fuzzing, fuzzing userland code and services, file passes, network services, all that kind of thing. And we'll also look at fuzzing kernel code, including kernel drivers and inbuilt, Windows operating system kernel code. And we'll also look at logic vulnerabilities. So, like privilege escalations and bugs through logic vulnerabilities instead of just fuzzing. And we'll also explore some actual live zero days as well throughout this training. Now, while this training focuses, significantly on Windows and x86 and x86 64, a lot of the learnings and the fuzzing and like everything we'll be doing is actually applicable to other platforms like Mac and Linux, and also other architectures like ARM. In fact, some of the fuzzing that I've done directly on Windows x86 64 processors, I've been able to directly replicate on like Android ARM64 devices. And that's because generally the approach to fuzzing and harness development and bug finding that we'll go through is pretty generic. It's generally a process that translates well to other platforms. Now, there's environment specific things you'll need to adjust for going between platforms or going between architectures, but the overall process and even what you're doing can generally stay the same. So a bit about me, security researcher at Microsoft. I've done lots of kernel and hypervisor and emulator dev, contributed to open source emulators like Box, primarily for the purposes of fuzzing. I've used Box to fuzz hypervisors before, and that's required me to add in specific features to Box to support that. And we'll go through emulation-based fuzzing a bit later when we look into fuzzing the kernel. But we'll also look into common fuzzers and how we can leverage existing common fuzzers for our use cases. So this first section agenda will cover a lot of the fundamentals of Windows and x86 64 that we'll need to go forward to jump into fuzzing. We'll get an introduction to fuzzing, what is fuzzing, the process of fuzzing. I'm exploring all of that. And then once we've done some initial fuzzing stuff, we'll briefly look at crash triaging. Now, this course isn't really focused on triaging crashes or exploiting bugs. It's about solely finding bugs, finding those 0 days. But I do touch on those other bits and pieces here and there. And then we'll kind of wrap up this section with performance fuzzing and thinking about performance, which is a major thing. A lot of fuzzing harnesses, which we'll get into later, is not performant. A lot of the default ones aren't performant. A lot of the ones that people design still aren't performant. There's a lot of bottlenecks and a lot of performance considerations we can make to make our fuzzers really stand out and get more iterations per second, find those 0 days faster, and just be a general, like a complete improvement over what it may initially be when we first develop it. We'll look at how to profile our targets, how to find those bottlenecks, and we'll come up with some really creative ways to speed up our fuzzing. And I'll also share some private files that I developed and that I use myself for performance fuzzing so that we can apply those techniques to the fuzzing that we'll be kicking off later on. So when it comes to finding 0 days, there's a couple of approaches. Normally it's a combination of the two, but we could split it in terms of static and dynamic analysis. By static analysis, I mean like, code review or just reverse engineering the target in like Ghidra or Binary Ninja or IDA and stepping through that line by line. Through dynamic analysis, I mean things like attaching a debugger to the running target and debugging the target and trying to find bugs by stepping through it in a debugger or manipulating it in a debugger. Typically, those approaches are good for smaller code bases or very specific functionality because you have to dedicate your time manually to analyzing, line by line type of thing. So it's very time consuming. But because you are like reversing it line by line, doing a source code review line by line type thing, you typically do get a good understanding, like a really good understanding of the target. Now, the problem as well with this is that it's one shot. It's a one shot type thing. And by that, I mean, if I analyze a parsing function to find bugs in it, and then a new version of it comes out, likely I'll have to analyze that new version the same way I analyzed the old version, which is line by line, all manual. Pretty much, the stuff I did from the first analysis doesn't carry over too much to the second version. Sometimes it does in little bits, like maybe I can diff the first version and the second version and only focus on the changes, things like that. But I still have to put in that manual effort on the second version, even if it is going to be quicker than the first version. Now that contrasts with the fuzzing approach. With the fuzzing approach, if we have a target that, maybe it'll be easier to visualize it. Let's visualize it for a quick second. If we have a target that exposes a function called parse PDF, and it takes a path to PDF file, right? Say this has an implementation. That implementation is like, move rex, the contents of RCX, blah, 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 ret. So that's the actual content of the parse function, right? So we have this parsing function. It's got its implementation there in assembly that does the parsing of the PDF and then it returns. Now, if this assembly part, so this part at the bottom here, right? If this part at the bottom here changes because, a new version came out, on the static analysis approach, I'll just have to manually reverse it and look through it line by line again. But on the fuzzing part, right, how do I fuzz this? Well, it's a function that takes a path to a PDF. So I can just generate PDFs and pass through the paths to the here, and it'll fuzz it. And if this implementation changes, well, nothing changes for me while fuzzing, right? I'm still calling it with just a path to a PDF. That interface, this API interface, does not change. So even if the implementation changes between versions, the fuzzer I wrote for the first version can just be run against every other version because the actual prototype of the function that we're interacting with has stayed the same. So that's what I call something like continuous fuzzing, right? Where you write a fuzzer once and you can update the target version over time, but you just keep running the same fuzzer. There's no need to change the actual fuzzer itself. Now, of course, sometimes we do change it to support new features and all of that sort of thing. But, it's a possibility that we won't have to touch it, or we'll only have to do minimal touches to it. Fuzzing is also good for complex code bases. And that's because generally you only need a good enough understanding of the target to get started. Again, let's come back here. If I wanted to find bugs in this in the assembly, and I was doing static analysis, I would again need to understand what's going on in this whole assembly block pretty much completely. But if I wanted to fuzz it, again, all I need is to know that this function exists and that it takes a path to a PDF, and that's it. I can immediately start fuzzing it with PDFs that I create. To get started in fuzzing there, it requires much less knowledge to get started. And even if the implementation was super complex, the interface isn't. It's just a path to a PDF. So I don't need to worry about the super complicated implementation it does. I can just call it with a PDF. So hopefully that kind of gives you an idea of how fuzzing can be quite beneficial for finding bugs. I guess I should also have started with what is fuzzing, right? Now, when it comes to fuzzing, we generally have some sort of target, and that target takes some sort of input that we can control or influence. Maybe it reads a file, maybe it reads a command line, maybe it reads some data over the network. It can be whatever, but it's something that we control that the target can, read or pass or do some sort of processing on. And the idea is that you create inputs and mutate or change inputs and feed it into the target to try and get the target to do something dangerous when processing the input and crash. So by generating an input, I mean creating an input from scratch. And by mutating an input, I mean changing an existing input. So in this example on the right, we could start with the input totally not a PDF. Now, if we wanted to mutate this, perhaps it only changes the not to is. So this becomes totally is a PDF, which isn't a completely newly generated input. It just took this totally not a PDF input and mutated it by changing some of it, right? That's the mutation phase, the changing phase. And then you feed that into the target in hopes that we find a crash. Why fuzz? This just reiterates the fact that some code bases are very complex. Think of network connections where you have this large state machine where it can be in a connected state, a negotiating state. It could be handling a specific sequence of SYN, FIN, or ACK packets. It could be in a closing state. And depending on what packet you send, on what state the machine's in, you could hit a whole bunch of different code paths. And there could be so many code paths to analyze here. It'd probably be easier and quicker to write a fuzzer targeting this protocol and run it continuously than it would be to statically analyze all the different code parts of this and how it changes depending on what state the network is in and all that kind of thing. Now we're going to look at some of the terminology. So I'm going to use words like fuzzer and harness and things like that, and we're going to clarify what I mean by those. Now, when I'm talking about a fuzzer, I'm generally talking about something generic to a point. It's usually platform or architecture specific, like it might be specific to Windows, or it might be specific to ARM or x86, but it's not generally target specific. What I mean by that is, say we have a few different targets. We have Adobe PDF Reader. That's one target. Next target could be Zoom. Maybe the next target is WhatsApp. And maybe we have another target that is, I don't know, Notepad++. These are 4 different targets. Now a fuzzer generally is generic enough to not care which target you're fuzzing. I can use the same fuzzer for WhatsApp. I can use the same fuzzer for Zoom, for Adobe, for Notepad, assuming that they're all on the same platform or architecture. Because a fuzzer might have the requirement that it's a Windows-only fuzzer, so it can only fuzz these if they're on Windows. Or it's an ARM and x86 fuzzer, so it can only fuzz them if they're on ARM or x86. It can't fuzz them if they're on RISC-V or some other architecture, like ARM32. And the fuzzer's purpose is to handle input generation, mutation, and saving interesting inputs. So generation is generating an input. So if Adobe PDF takes a PDF file, well, if the fuzzer isn't really smart, it might just generate an input of random bytes, save it as input.pdf, and feed that into Adobe PDF Reader. If it's smart, it might have some logic to generate a valid PDF and save that as input.pdf and feed that into Adobe PDF Reader. Mutation would be grabbing an existing input, like this first one, and just changing it. Maybe it changes the 2 to a 1. Maybe it changes 32 to 24. Maybe it changes 98 to A. just making slight changes. That's the mutation part. And then the saving interesting inputs part. Now you might wonder, what is an interesting input? Now, there's different ways of defining what an interesting input is. A common way that we will be taking advantage of is by code coverage or coverage feedback. Now, let's take a look at what this might look like. Let's start with source code. Say we have some source code that says file buffer equals to read file on file path. And then there's if file buffer 0 equals to 0x41, return 1. Else, return 2. Okay. And say file path contains an input. So it contains input 1, which is 0x41, blah, blah, blah. And then say we have input 2 that is 0x, blah, blah, blah. Okay. Now, say file path contains on our first run input 1, and then on our second run input 2. Now, we can use code coverage to visualize or track which code blocks have been hit from our input. So let's track input 1. Input 1, well, you know what? We can do them both at the same time. Will input 1 and input 2 hit this first line? Yes, it will, right? Actually, before I do that, let me change input 1 to yellow. Let me change input 2 to blue. Okay, now the code lines that only are hit by input 1 will be yellow. The code lines that are only hit by input 2 will be blue. And the code lines that are hit by both input 1 and input 2 will be green. Now, the first line of file buffer reading the file path or reading the bytes from the file on disk, both inputs are going to hit that line because there's no conditional there, right? They're both going to hit that line perfectly fine. So let's color that green. Now, this if check, both pieces of code are going to hit this if check. They're both going to check if the first byte in the buffer is 0x41. So that's going to be green. However, only input 1 has the first byte as 0x41 right here at the start, right? So only input 1 is going to satisfy this check of the first byte in the buffer being 0x41. So this path here is going to be yellow. Whoops. Let me try that again. Now, yellow input 1 is going to hit this if block here and it's going to return 1 and that's it. Input 2, on the other hand, isn't going to hit this first if check because it doesn't pass the condition of the first byte containing 0x41. So instead, the input 2 is going to hit this second block. Cool. Now let's introduce an input 3. And input 3 is going to be similar to input 2 in that it's not going to satisfy the first if check. Now, what we see here, what we're visualizing here, is that all three inputs will hit the first line and the second line. Only the first input will satisfy the check and go into the curly braces and hit the return 1 line. And inputs 2 and 3 will both hit this else block and return 2. Now, say our fuzzer runs input 1, and then it runs input 2, and then it runs input 3. And it's got this database of interesting inputs that it saves. Now, when it runs input 1 is going to hit whatever it hits, but because it's the first input, it's going to have the coverage that's unique. It's going to have this first line, this second line, and this if condition in the middle. That's the coverage that the input 1 is going to hit. And since it hasn't run anything else, that's the first time it sees that coverage being hit, and it's going to save it. So it's going to save input 1. You know what? Let's remove the background color for this. Okay. I don't want it to be blue. I really don't want it to be blue. And let me force it white. Oh, bloody hell. Let me try that again. Okay, there we go. All right, so it's going to save input 1. Now we run input 2. Input 2 also hits unique coverage. Input 2 is going to hit this else block, right? It's going to hit this else block at the bottom and return 2. And before input 2 has run, the fuzzer has not seen that else block be hit before because our first input did not hit it. Only our second input hit that block for the first time. So it's going to save input 2 as an interesting input. Now, input 3 doesn't hit any unique coverage. It hits coverage that we've seen before. It hits the first 2 lines, which both input 1 and 2 have hit before. And input 3 hits this else block and returns 2, which input 2 already reaches. So since input 3 doesn't reach any new code, it's not going to save it as an interesting input. Now, this is how code coverage guided fuzzers, well, how they work, how they use coverage. They save the interesting inputs that hit new coverage. And then when they do the mutation phase, they will mutate inputs from their interesting inputs database. That's the goal. Now, of course, we're visualizing this as as code here. But the fuzzer isn't going to see code, it's going to see assembly. But it's the same concept. We'll have like, I really don't want this to be green. Actually, you know what? Like, it could be green. You'll have like comp, say byte pointer racks with 0x41, and then jump 0 label 2, and then move AL 0x2 and ret, and then we have label 2, move AL 0x1 ret type thing. Now this line, every input hits the comparison check. Every input is going to hit this jump instruction. Only the inputs that fail this comparison are going to reach this line, and that's going to be input 2 and 3. So this line's going to be blue. And only the input that satisfies this comparison is going to hit label 2, which is going to be input 1. So we have input 1. And that can be an example of how it will be visualized in assembly, which is what the actual fuzzer will see. You'll see the compiled bytes and which bytes get hit in the target we're fuzzing. And another use for this is we can take this and we can visualize the coverage ourselves in tools like Ghidra, Binary Ninja, IDA, etc. And we can see what's going on. Say this label 2 is never hit, right? Say we're doing heaps of fuzzing, label 2 is never hit, all of our inputs fail the check. So all of our inputs fail the check and just return here, and we never hit the label 2 code block. If we see this as a result of our fuzzing, we can see which parts of the code we're not hitting. And then we can find out why we're not reaching that. Maybe our input, just for some reason, the first byte is never equaling to 0x41. What we can do there then is we can modify our fuzzing harness or our corpus, which we'll look at later, which is our inputs, and unblock our fuzzer from reaching this second code block, such that when we run it again, we will reach this second code block and we'll have expanded our coverage. And then maybe because we hit the second code block, we find a bug that only exists when the second code block is taken, for example. Right? So visualizing your coverage feedback like that can be very useful for seeing how effective your fuzzing actually is, how much of the code you're hitting, if you're being blocked anywhere, all of that type thing. And I guess I'll quickly go on it now of how we actually get that feedback. Now, typically it's implemented in a sort of bitmap. I'm going to quickly go through my favorite way of visualizing or logging that coverage, and that's via module name plus offset. So say we have the binary Adobe PDF.exe. Now, as you might know, because of ASLR and things like that, each run of Adobe could be loaded at a different address. Maybe the base address on the first one is 0x18,000. Maybe on the second run, it's 0x14,000. Maybe on the third run, it's 0x11,000. And then say I load it up into Ghidra, and Ghidra loads Adobe PDF at the base address 20,000. Now, when we're logging which bytes we hit in Adobe, well, first of all, you can see how, because of ASLR and things like that, the process may be mapped into different starting addresses each time it's run. But let's just deal with one for an example. Let's say we're fuzzing, and during our fuzzing, its base address is 11,000. Now, say we get a list of the coverage that's hit, and we get that address 11,232 is hit. We get that address 0x11,300 is hit. We get that address 0x11,304 is hit. Right? I get these lists of coverage that was hit in the target during our fuzz cases. Now, say I want to visualize what instructions they were, or what code blocks they were, or where they lived, and what the purpose of those code was when I load up Adobe in Ghidra. Now, I can't just browse to 0x11232, for example, right? Because 11232 means something completely different in the fuzzer binary than it does in my Ghidra analysis view. That's because Adobe is loaded into the base address 11,000 when I was fuzzing, but it's loaded into the base address 20,000 in my Ghidra view. So the addresses are going to point to completely different things, or just be even completely invalid in one context versus the other. So instead, how we can format this is via module name plus offset, where the module name is the replacement for the base address, and the offset is the address minus the base. So the offset for 11232 is 11232 minus 11,000, which is just 0x232. And the module name is Adobe PDF.exe. And we can do Adobe PDF.exe plus 0x232. You know, this one's that, this one's that. So this will be Adobe PDF.exe plus that, and Adobe PDF.exe plus that. Okay. So now we've replaced the base address with Adobe PDF.exe plus the offset. In this case, the offsets have translated to 232, 300, and 304. Now in Ghidra, instead of doing 0x11232, that becomes Adobe PDF.exe plus 0x232, which we can then expand the symbol Adobe PDF.exe to be the base address of Adobe PDF.exe in our view, which becomes 20,000 plus 0x232, which equals to 20,232. So now if I go to address 20,232, I'll see the same byte that was in 11,232 in the actual live run of the target. So you can see how module name plus offset can be a nice portable way of logging the coverage and then transporting that and being able to view that even in other tools, even where the module, whether it's an executable or if it's a DLL or whatever, is loaded at a different base address. The module name plus offset is a portable representation of, the location in the binary that we're referring to. Now note that this is very, very, very target specific. For example, this is going to be valid for a very specific type build of Adobe. Maybe build, 2123-1200 built on the 1st of Jan 2023 or something, right? That's where this offset is valid, which means in Ghidra, if I want to convert the offset plus module name or module name plus offset, I need to make sure that Ghidra is analyzing the exact same version of the target. If it's a different version, if this is version 2124 that's built on the 5th of Jan 2023, because it's been recompiled, because they're different versions, the offsets may change, which means the module plus offset referred to in the left-hand side version may not be the same as the offset and module name in the right-hand side version, because they're two different versions of the target. They were compiled differently. The compiler could have moved around things. Things could have changed. The offsets aren't going to be referring to the same thing anymore between them, or it's very likely that it won't be. So you need to make sure that you are analyzing the exact same version between these. Cool. And of course, a fuzzer is responsible for catching and reporting crashes, right? There's no point fuzzing something if we don't have a way of actually catching and, detecting and reporting those crashes. Now, when I'm talking about a harness is the target specific code. So we saw that a fuzzer was generic, right? If we go back, if we had these 4 targets, right, a fuzzer can be pretty generic across them. A harness is going to be very specific. Let's take Adobe PDF again as an example. A harness, so an Adobe PDF Reader harness might target Adobe PDF Reader version 2132.1200, compiled on the 1st of Jan 2023. So again, the harness is a target specific code. It's specific to a very specific version of the target. Generally anyway. And the reason for that is because the harness handles feeding the input into the target. Let's walk through Adobe again. It's a fun little example. Say we have, Adobe PDF.exe. Now Adobe can read and pass PDF files. Now say I'm generating PDF files that I want to fuzz in Adobe. I want to fuzz Adobe's PDF parser, which means I'm going to be generating PDF inputs. I want Adobe to process those inputs and see if it crashes. How do you do that? Well, how do you open a PDF in Adobe? Well, you can, open Adobe PDF.exe. You can click File, click Open, click your PDF file. Right. To get Adobe to parse a PDF, I can open Adobe. I can click the File tab at the top left, click Open, click on my PDF file, and Adobe will parse my PDF. How the hell do you fuzz that, right? If I generate a whole bunch of PDFs to fuzz, am I going to sit there clicking File, Open on individually each of the PDFs that I want to test? I'll probably be going through like one PDF file every 2 seconds or something. That's horrible. Absolutely horrible. That is not how we fuzz. So this is why we write a harness. So for example, most code, like Adobe, like everything else, sometimes the functionality to parse a PDF may be in the executable, and we can work with that too. But a lot of the time, it's in a different module. Because Adobe PDF has a lot of functionality, right? It's got the GUI code to actually give you the GUI. It's got networking code. It handles, storing signatures. It can pass images, not just PDFs. It can convert things between different formats. It can print things. It's got a like JavaScript interpreter inside or something. There's a lot of different parts to it. So likely they're going to split up into DLLs. So say when you actually click your PDF file, what happens is Adobe loads a DLL, and that is going to be PDF parser impl.dll. I don't want any background. Gonna have to make this a bit larger. Okay. And this DLL contains a function called parse PDF that takes a file path. So say what happens when you actually click your PDF file is Adobe PDF passes the path to your PDF file to the parse PDF function that lives in this PDF parser impl.dll. And this DLL in its parse PDF function opens your file, parses it, presents it on the GUI or whatnot, and then returns to Adobe. If this is what happens, then we don't actually need to bother dealing with Adobe at all. Why can't we just call parse PDF that lives in the PDF parser implementation? That's what Adobe does. If we find a bug in parse PDF, we'll be able to trigger it by opening up Adobe, clicking our PDF file, and Adobe will pass through that information and call this parse PDF function in this DLL for us anyway. So that's our process for fuzzing. We have our harness. Let's call our harness my Adobe harness.exe. And what does it do? Well, it loads a DLL. What DLL do we load? Of course, we load the PDF parser DLL. With that DLL loaded, we get a pointer to the function parse PDF that lives in that DLL. Now, when our fuzzer sends us the path to new fuzz input. So we have the fuzzer. The fuzzer is going to send to our harness the path on disk to the new fuzz input, which is going to be some PDF on disk that the fuzzer created or mutated that we want to fuzz. Our harness will get that path, and it will pass through that path to the parse PDF function with a file path here reflecting the path we obtained from the fuzzer. That parse PDF function, which lives in this PDF parser impl DLL, will do its thing. It will pass the PDF and it will return to us. And then the fuzzer will give us a new input and we'll pass through the new input to parse PDF. It'll do its thing, return to us. We'll get the next input. We'll pass through the next input to the PDF parser. It'll do its thing and it'll return to us. And if we get an input that crashes parse PDF, we should be able to replicate that crash by opening Adobe, going File, Open, and clicking on the file on disk that caused the crash. Because Adobe is going to do what our harness is doing. It's going to call parse PDF on the DLL, parse it, it's going to crash, and we just crashed Adobe. The benefit of doing it our harness way is our harness can be completely GUI-free. There's no need for a GUI. It gets the path from the fuzzer, so it's not getting it from File, Open, and clicking the PDF. It's getting it automatically as the fuzzer generates inputs. There's no need for manual intervention. There's no need for us to click things in a GUI. This is all going to happen automatically. The fuzzer is going to generate new inputs continuously and give the path of it to the harness. The harness is going to feed those inputs into the pass PDF function continuously and return. And we go from this initial way of manually doing it and probably getting like 2 fuzz cases or like 1 fuzz case every 2 seconds to doing it programmatically this second way and probably getting 100, 500, 1,000, 2,000 fuzz cases per second. Much, much faster, much, much nicer. So that's the purpose of a harness. The fuzzer can be pretty generic, generating inputs and mutations. The harness is very specific. It knows how to feed the input to the target. It knows that the target function lives in this DLL, so it loads that DLL. It gets a function pointer to this pass PDF function. When it gets the input, it calls that function with the right parameter to trigger the passing of the PDF. So that's the harness part. Now, fuzzers can be expanded with custom generators, custom mutators, that type of thing. For example, say the fuzzer, by default, when it's generating PDFs to fuzz, it's just generating random bytes. They don't really follow a PDF format. They're just random bytes, and it just throws it in and sees how far it gets based on coverage. Since it does have that coverage guidance, it can improve its inputs, because if it somehow formulates a valid PDF header, that's going to pass like a PDF header check in the target, which means it's going to hit more coverage, which means that input that passed that PDF header check will be saved as an interesting input, and will build on top of that input in future fuzz cases via mutations. But we can define a custom generator that actually knows how to formulate a PDF. Say a PDF, it's pretty much is just a structure, right? Say it's got a PDF header, which is the set bytes. Now, I'm just making this up as an example. I don't know what the PDF structure is, but you would figure it out by just reading the RFC or figuring out, what a PDF's prototype, protocol or structure is. Like, it's got to be a well-defined format, because there's lots of tooling, including open source tooling, that can create PDFs. And to be able to create PDFs, they need to know what the structure of a PDF is. So if you can't find documentation online, try to find an open source tool that creates a PDF and just look at the source code. How does it construct the PDF object? Maybe it has a header that's defined by the bytes 0x1337. And then it's got some sort of data, and then it's got a PDF footer that's 0x6951. Then we can define a generator or mutator for our fuzzer that says, that says, well, you got to follow this format. The header of our input, or the first, say the header is 4 bytes, and the footer is also 4 bytes. Then we can say the first 4 bytes of the input have to be this magic header value. Then you can fill the rest of the buffer with whatever the hell you want. And then the last 4 bytes of the input have to be this magic footer. And then that's our custom generator or mutator. It follows that rule. And then that can go in, and our inputs will always follow that format. You can also say that it's 4 bytes, and if you can make it slightly more intelligent, you can say that it's 4 bytes, then it's got some var that's 2 bytes, and then some var 2 that's 8 bytes, like this. And what this will do is, even though it's just some arbitrary 4 bytes, 2 bytes, 8 bytes, since you've made it as just, this isn't just like 8, this isn't just like, a blob of like 14 bytes or some shit. This is actually made up of 4 bytes, 2 bytes, 8 bytes. So the mutator may just say, I'm going to mutate just this variable, so it mutates these 8 bytes. Or it's going to mutate just the header, so it mutates just these 4 bytes. Or it's going to mutate some var, so it mutates just these 2 bytes. it's able to isolate the variables and just mutate it, like just mutate this variable or this variable or this variable. If you didn't have this structure defined and it was just some arbitrary 14 bytes, then it might actually mutate bytes that aren't just limited to one variable. So it might mutate the last, it might mutate 3 bytes coming from the last byte in the PDF header. So it mutates the 4th byte in the header and the 2 bytes of some var. So the mutation phase mutated these 2 variables, which, it can be fine, but if you actually define it as a proper structure, it makes more sense. This comes into play a lot more if you have something constant in between. So you have constant magic that's 0x1337. So say you have a structure where you can have 4 random bytes followed by 2 random bytes followed by a hard-coded magic 4-byte value of 1337 followed by 8 bytes of whatever you want. If the fuzzer knows this, it knows that it can mutate the first 6 bytes and then the next 4 bytes it has to have a magic 1337 value, and then the 8 bytes after that it can modify to whatever it wants. And it can stick to this structure, which is good because if your target is something like, say your target first does if magic does not equal to 0x1337, ret, else, pass other vars, for example. Then if the magic isn't the hard-coded value, then we're just going to be missing so much functionality. We're going to be wasting a lot of our fuzz iterations. So defining a structure like this can be very useful, and we'll look into that. So fuzzing can also be just feeding random inputs into targets, even with no coverage feedback. This actually can still find bugs today, but we're going to be focusing a lot on smarter fuzzing, coverage-guided fuzzing, full system snapshot fuzzing, things where we can view the coverage from our fuzz cases, see if we're blocked on things and things like that. But I just want to kind of point out that we can still find bugs the dumb way too. So there's also grammar-based fuzzing, which is very similar to the structure view that I went through before. We can define tags that have values. So this is very much used in JavaScript fuzzing, browser DOM-based fuzzing, where here we have an identifier tag, which can be a const, an identifier tag, which can be a static, a var name, which can be my value, an int32, which can be a range of values from 0 to 0x FFFF. And we can have an int32 variable, which consists of the identifier tag, space, var name tag, space, equals, space, int32 tag. Which means based on the grammar above, a grammar-based fuzzer may generate an int32 variable tag, which can be resolved to an identifier, such as const, a var name, such as my value, space equals space, and then an int32, such as 1337. And this could be like JavaScript or C or something, like a valid input for something we're fuzzing. So if we look at this based on existing fuzzers, just to give you an example, if I look at Tomato and Fuzzily, Tomato and Fuzzily are both by Google Project Zero. Tomato, for example, is a grammar. It's got HTML tags that it lists out. It's got a grammar.py that says, int ranges. Well, if you have an int, it could be from this range to this range. If you want to generate an int32, it's that range to that range. An unsigned int32 is going to be from that range to that range. An unsigned int64 is going to be from that range to that range. Defining the types. Short, long, DOM string, boolean, float, double. Lots of logic for generating them. It's got the generator that can pass tags by getting, tag equals to random.choice from a HTML type. So it gets some tag, gets a tag type, gets a var name, starts creating HTML elements based on the tags. It's got the logic there. If you go under rules and you go under CSS properties, here's some rules for CSS. We have CSS property gradient includes the tag color, comma, space, tag color. We have HTML, which says that an input type can be a date, an input type can be a color, an input type can be a checkbox. And, based on all these definitions, it just can chain them together to be able to generate valid HTML files or JavaScript files based on this kind of grammar definition that tells the fuzzer how to generate valid HTML or JavaScript files. And then you can have a browser try to run that JavaScript or HTML file. And if it crashes, well, you just got a DOM-based 0-day in the browser. Now, we're not focused on browser fuzzing much here, but, just grammars in general are good to be aware of, so you can kind of explore that in your own time a bit. We will look at like some structure-based fuzzing a bit later. There's automated grammar-based fuzzing. This is something like syscaller. Let's go to syscaller, which is also on GitHub. Now, under the Windows section, there's windows.txt. This tells us functions. So say, let's look at delete file A. If you want to call or fuzz the delete file A function, you need to create one parameter, which is a pointer. If you want to call the find close function, you need to pass through one parameter, which is a handle. If you want to call the find first change notification function, you need one parameter, which is a pointer, a second parameter, which is an int32, a third parameter, which is an int32, and it returns a handle. So that defines what you need to provide to call the function. And then you've got like constants here, which say, well, these are constants for some parameters. So if you want to generate a create always, you need to pass 2. If you want to generate the create 1, you need to pass through 1. It also says there's a resource, which is a handle. It's defined as a resource because you get a handle from calling other functions, right? If you call create file, then you get a handle. So that's going to be a resource. Some definitions here for things. Again, it's just another way of generating a grammar. Syscaller uses it as well. We're not going to explore syscaller too much at the moment, but it's also good to know that that also does some really nice kind of like grammar generation stuff using what they call syslang. And this grammar can be automatically generated if you have symbol information like a PDB or dwarf symbols or cough symbols, because those symbols can have information on like what structures are and what their underlying types are. And syscaller can like pass those symbols and generate a grammar automatically based on that symbol. Or you could write your own tool to do that as well, really. I kind of mentioned before, but like most fuzzers come with some generic mutation strategies of just like flipping bits, taking byte slices, taking multiple inputs that are saved and like splicing them together, inserting magic values like the max value of an int and things like that into your inputs. Just very generic ways of modifying an input. And then based on the coverage feedback, they may get further in the target and they may save that new input. We kind of talked about coverage feedback already. Okay, we have something called corpus. Corpus just means some sort of inputs. When I say initial corpus, that's going to be your initial starting set of inputs. And that generally determines what code you'll hit. For example, say we have a image parser. It can pass PNGs, it can pass JPEGs, it can pass SVG files, etc. Now, say with our fuzzer, we start with an initial set of corpus. So our initial corpus, which is our starting files that the fuzzer can mutate to begin with. And say we start with just test1.png, test2.png. Now, our fuzzer can grab these inputs, mutate them, and feed them to the image parser. Now, if, for example, a PNG format is very different to an SVG format, say a PNG, now I'm making this up just for the case of an example. Say a PNG has the header 414141. SVG has the header that, which is a very long header. Now, our initial corpus will have a valid PNG header because our corpus is going to be valid PNG files. So they'll pass through the header check and fuzz deeper into the image parser. But if we try to fuzz the SVG parsing functionality of the image parser, our corpus is very unlikely to hit that branch of code because it's going to check our header against the SVG header and it's not going to match up. And it may be hard for our fuzzer to mutate our header enough in a single go to kind of, well, potentially a single go. Potentially not, depending on how the checks are done. And we'll explore that a bit later too. But without starting with an SVG file as our corpus, it may take a long time for the fuzzer to generate a valid SVG header in our corpus to be able to hit the SVG parsing code. But if we started with test3.svg, which had that header set, then when our fuzzer runs test3 to the image parser to begin with, it'll hit that SVG parsing code. So they'll be saved off as an interesting input. And the fuzzer can mutate that SVG code, including mutating bytes that aren't the header. And this way, we'll have inputs that will fuzz the PNG parser, and we'll have inputs that will fuzz the SVG parser of the image parsing, which means we'll be overall in total hitting more parsing code in the target. We'll be hitting both the PNG and SVG parsing code. So your initial set of corpus is very important as it can kind of determine the likelihood of you hitting the different parsers and different code branches in the target. And there's multiple tricks or methods for obtaining or generating corpus. If it's a common corpus type like PNG, you just pull it from the internet. If it's some obscure type, but there's like documentation on the structure of it, there's an RFC for it, you can write your own code to generate valid inputs based on the RFC. Like if you know that the structure of this input has a defined header, then it's got like some bytes, and then it's got a defined footer, you can write some code that generates inputs that has that defined header, and then the bytes in the middle, and then the footer. Now, that kind of concludes the start bit of theory. Next, we'll go through what ultimately is a crash, what a crash looks like, how we are detecting crashes, how the actual operating system, how Windows and CPUs detect and handle crashes. And this is important to know because there may be some things to consider on how a crash is detected that may influence how we fuzz or how we interact with the binary. Because there's some type of vulnerabilities that can manifest in a crash very quickly, and there's some types of vulnerabilities that don't immediately manifest as a crash. We're going to look at the very low-level implementation of this in the CPU to find out why that is and how we may be able to compensate for that a little bit.